Good afternoon, everyone. Uh, let's start. So we just have 3 more lectures to go, right? Including this one. So today we're going to finish with single hydraulic fracture models, and then we're going to continue with multiple hydraulic fracture modeling and design. From Monday, if you remember, we finished talking about modern hydraulic fracture simulators. And I just want you to remember that everything that is in there is mechanics, about to see how fractures are going to be contained in the vertical direction. Of course, we know that those are going to be mostly perpendicular to the minimum principal stress. And in order to see how far the fracture goes, how quickly it grows, in addition to that, we need to add fluid flow. We need to add fluid flow in the fracture. Yeah. It's going to come on just in a minute. And I'm not writing anything new. Don't worry. Just a few words. Okay. So then we put everything together: hydraulic fracture height, fluid flow into the fracture, either a fracture in fluid or a proppant. You consider the fracture opening. You consider other things as leak off. And then you put everything together into a blender, and then you get a hydraulic fracture simulator. If you spend enough time, I'm pretty sure that you can do your own. It's hard, but it's not that complicated. At least the physics, everything that goes in there, you already know that. And I wanted to show you a few examples about how these hydraulic fractures look like, at least from a simulator point of view. And we'll talk later about what real hydraulic fracture looks like. And for that, we started to talk about this software. This is one example of a software that predicts hydraulic fracture height, width, and where proppant goes. As you can see, we have a well log, and based on that well log, you build a stress log. Based on that stress log, you will know how far your fracture is going to go in the vertical direction. And depending on how much you inject, you know how far your fracture is going to go. And depending on the pressure which you inject, you will know also what is the width of your fracture. We also talked about this other piece of software, and here we have multiple stages. We're going to talk in a bit about that, but what I want you to see out of here is that notice that what you see in color is the fracture width. So fracture width, it makes sense that it's bigger at the wellbore, and then it gets thinner and thinner. But notice how the fracture height is not constant, but it's variable. It gets into these little fingers that are places where the minimum principal stress is the lowest. So that's where it propagates. And I think there was a better example somewhere over here. Yes, you can see, like, for example, these ones over here, it grows quite thick close to the wellbore, but then as it goes further away, it just concentrates into some layers that apparently have a low stress. So the fracture is always going to look for the minimum principal stress, find the direction, and that's how it's going to propagate, always perpendicular to the minimum principal stress. And then it's going to look for places where the minimum principal stress is the lowest, and that's where it's going to propagate. I think this is a nice figure also to discuss about hydraulic fracture propagation, because many times people say hydraulic fracture propagates in the direction of SH max. And probably in this case, you can see that that's true if you look from the top. So SH mean will be in the direction of the wellbore. SH max will be perpendicular to it. And it is partially true that the fracture propagates in the direction of SH max, but also propagates in upward and downward direction. So I think it's a lot better to say that hydraulic fracture is going to propagate in planes perpendicular to the minimum principal stress, which is true for all what we see over here, and it's going to be sweet spots for low minimum principal stress, and that's in the places where it's going to go and it's going to fill up. And I have one more example about that. Let's see if we find some nice images out of here. So this is another case. You can see how hydraulic fracture, the hydraulic fracture height is variable. Here there is another case. And I have one more piece of software which is relatively new. And I was looking for a video, but I couldn't find it. But let's play this one. Okay. We didn't get into this so far, but we'll talk about this later on. This is a hydraulic fracture completion of a horizontal wellbore with multiple clusters. So the fractures might grow simultaneously. Let's see. Here on the left, you have apparently fracture pressure, aperture, and then here we have on the bottom right, you have proppant total volume. So let's see what's going on. The fracture is starting to grow. Okay, what do you notice here at the very beginning? In which direction are the fractures growing? Some of them. They're growing up, right? And let's continue playing the video. You see, for example, this one looks like a Mickey Mouse. It's growing up, these two. And in this case, for example, also you can see the proppant. The proppant is not going all the way over the fracture, but it's mostly concentrated at the bottom. So this one will be a case in which the fracture is also propagating in the direction of the minimum principal stress, because in this case, apparently, the minimum principal stress is decreasing as you go up. And that makes sense, because stress almost always decrease, at least the main train, as you go up. And that's what hydraulic fractures are going to do as well. In some cases, as this one, you can see this one goes down, probably because this one goes first, and it went down. But again, I repeat, you put fluid flow into the fracture, leak off into the porous medium, and if you know what is the distribution of the principal stress in the subsurface to begin with, then you can understand and you can model where fractures are going to grow. I'll look for that later on. All right, so I think this is a good introduction. We talked about single hydraulic fracture models, and let's talk about multiple stage hydraulic fracturing. So in a single fracture, we just care about one fracture, and then that's it. But when we have multiple fractures, we'll see that the problem it's not the same, and it might be a little bit more difficult. Okay, first of all, why do we do multiple stage hydraulic fracturing? What is the main advantage of doing multiple fractures? Any idea?
So that it's more even.
It's more what?
It's more even because if you were to fracture everything at once, then some parts will receive more pumping fluid than other areas. Further down you go, I guess.
Yeah, but I mean, what's the principal? What do you gain from that? And I want to compare, for example, in the same formation, you could either drill a simple wellbore with no hydraulic fracture. You could drill a vertical wellbore with a hydraulic fracture, or you could drill a wellbore, kick a lateral out of it, and put multiple hydraulic fractures in it. So I'm just going to draw one right now, but imagine that you have multiple hydraulic fractures there. In a single wellbore, what will be the area of the reservoir in contact with the wellbore? Let's assume an open hole completion. It just will be the area of the wellbore, right? So that's going to be, for example, 2 pi, the radius of the wellbore, times the height of the pay. If you have a single completion of a hydraulic fracture, now let's say that this is the length of the fracture, then you're going to have, I'm drawing here just one wing, but that is going to be then 4 times the length of the half wing times the height of the fracture times and no, that's it. So the area of one side will be HF times XF, more or less. You have 2 sides, then that's going to double it, and then you have 2 wings, then that's going to be 4. And if you were to make multiple fractures, the main advantage is that now you're going to have a lot more of surface area in contact with the wellbore. So let's imagine that we put another fracture here, there, 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 and there. If you have multiple fractures, ideally, we have seen already some simulations that this is not quite like what I'm drawing, okay? But let's assume for now, just for simplicity, that this is going to be the case. This is more or less what we will get. And now the area of this multiple stage hydraulic fracturing of the rock in contact with the wellbore or the main hydraulic fracture then is going to be each surface of the fracture, which is XF times HF times 4, because that's what it will make a complete fracture. But then we have to multiply times the number of fractures. And the number of fractures is going to be equal to the length of the laterals divided the distance between each fracture. So now we have 2 more additional parameters that we can control compared to a single hydraulic fracture completion. Single hydraulic fracture we just design for the fracture length, and the fracture height, it depends on the formation and your net pressure. but it's going to depend mostly on the formation and where is your pay. But now we have two more numbers to control: the length of the lateral and the spacing between the fractures. So let's do a quick exercise. I'm going to tell you here that let's imagine a pay, just to make some numbers and to have an idea about what these numbers are. The pay is 100 feet. The radius of the wellbore is ½ foot. The length of the lateral, let's say it's 5,000 feet. And that's not too long. Some wells get to 10,000 feet easily or more. We're going to say that we're going to design these fractures to have 500 feet of length, of fracture half length, and last, the spacing between the fracture is going to be 50 feet. Can you tell me, please, can you calculate what are going to be these three values? The area of a single wellbore, the area of a single fracture, and the area of multiple fractures. And I'll give you a few minutes to do that. So it's just a simple calculation. And let's see who doesn't have extra points yet. Me say yes. You think you can give me these values? Rogma, yes. You think you can calculate these values for me? Tell me the one of the wellbore. Let's do all the calculations first on square feet, and then we'll move. Okay, 314. What is this area like? It's the area of what? More or less, just to have an idea with something that you may know. Do you guys, what's the square footage of your room if you live in a dorm? It's about that? No? Smaller, probably half of that? Probably, you know, a regular, like in apartment is about 1,000 square foot. So this one is about the size of a big room. Probably, you know, this room has an area bigger than that. Probably double than this one. But this is relatively room. It's like it's relatively small. It's the size of a room. Okay. What about SS? Who calculated SS? Anyone? Yes, Mr. Patel. How much? 200,000. Okay, this is a lot bigger, right? And what about the multiple? Mr. Rove? 20 million, okay. So, okay, let's talk about this one. So this one is more or less the size, square footage of a room. And this one, it's the size of how many football fields? A football field is about 57,000 square foot. So this one is about 3 and something, right? 3. Can anyone make that number? 2000 divided 57? That should be 3.5. Okay. So 3.5 football fields. And this one now is 100 times bigger than that. So it's 350 football fields. So we're talking about a very large difference here when we're making a hydraulic fracture. You can see the area is huge. Now, before we were talking about the size of a room. Now we're talking about the size of several football fields, and now we're talking about hundreds of football fields when we have several fractures. Okay, well, in an ideal world, or with these ideal fractures, it may be as simple as that, but it's not as simple as that. It's a little bit more complicated. First of all, even if we just had single planar fractures, at some point it may not be convenient to put so many. And that's why this design factor, the distance between fractures, is going to be very important. The length of the lateral, that's something that sometimes you want to maximize as much as possible. And as I was telling you before, today easily you have wellbores of 10,000 feet of length. But what is very important is the length between the fractures. So in principle, if you had these fractures more closely spaced, you will have more surface area. But what is going to be the problem with that, of having too many fractures? Let's assume for a moment that they will not hit each other, but you're right, they will hit each other. Yeah, Ms. Ruhana. That's also a problem of interaction. But I'm thinking more here in terms of cost. So the more fractures you have, the more costly this is going to get, right? Because you have to pay for each of those. So the higher the number of fractures, the lower your MPV is going to be when you consider just the cost of the fractures. Let's see if this turns out all right. I was thinking about this graph today. And on the other hand, if you have more fractures, probably you will have more production. Because, and let's assume the fractures don't hit each other for a moment, but they would. But the more fractures you have, then the more production in principle you will have. So your MPV will tend to be higher, and this would be what comes from production. But eventually, if you have then too few fractures, it doesn't cost as much, but production is not great. Eventually, you're going to have an optimal value that is going to optimize the number of fractures in terms of cost and in terms of how much production you're going to get. So my whole point about calculating the area is that the bigger the area, the more production you're going to have, but there is going to be a limit for that. And one is just related to cost, and then we're going to see now how that is related also to interaction between fractures. So you could also think this problem as, one student also gave me a very good example. Like you could think this wellbore as a closed line. and you're hanging your clothes there, right? So if your clothes are wet and they are too close to each other, probably they're going to take more time to dry up. If your clothes are a little bit further to each other, then probably they're going to dry up more quickly. So putting too many fractures very close to each other sometimes it may not be that great. But let's see now how that is going to be from the point of view of interaction. And so far, and that's one of the problems with some of the simulators that we also saw before, is that they assume planar fractures. And sometimes fractures are not planar. And they start to deviate as you make another fracture. So let's see how that works. And that's fracture interaction. Let's imagine that we have a wellbore, and we're gonna start with a single cluster completion where I put the cluster over here. I plug this section and I start to grow a fracture. Let's assume that this from a top view, we grow a nice fracture that goes into the two directions. It's filled with propant. It's perpendicular to the minimum principal stress. And then we're done with the first one. All right, so what do you think is going to happen with the rock that is adjacent to the fracture? If you had an initial state of stress that was SH min and an initial intermediate stress that, let's say in this case, is SH max, when you put the hydraulic fracture, what is going to happen with the stress near that fracture? You think would it be the same? Would it change? Remember that all of this is rock, so when we put a fracture, we are compressing the rock near the fracture. And that compression is going to create an additional stress near this fracture, that if you put the fracture too close, let's say that now we move over here, we put another set of perforations, you plug it again, you grow another fracture. If the interaction of this fracture is enough to affect this one, it could make this fracture to grow further away from this area of high stress. And why? Because now the stress that you have in this location is not the same that you had before. So the fracture is growing under another type of stress condition. And the minimum principal stress probably in this case is not anymore, let's put some coordinate, let's put the coordinate system here. Let's say it's not more now in east-west direction, but somewhere over here it's a little bit inclined because of the additional stress that you have. And if you go ahead and continue and make another fracture, probably now this one is closer than the other, let's put numbers. Number 2 is going to be closer to 3 than 1 was to number 2. So this may cause even some other types of fracture interaction, and you could have even fractures turn the other direction and hit the previous fracture, which is not going to be good because it's not going to be achieving the objective that you were planning before, is that extend the fracture as far as possible. And let's continue. Let's put another one over here. Probably this one will grow a little bit better than before. But if the effects are too high, again, if fracture distance is too close, sometimes also you can have these fractures just to grow just a very short distance, and that's also not going to be good. Okay, so this problem of fracture interaction is called regularly stressed shadow. And that's going to affect what is a minimum distance at which you put a fracture. Because if you want to put them too close, then they're going to affect each other, and that's not going to be good. And what is that distance is going to depend on what is your net pressure. The higher the net pressure, the higher is going to be the length that you need to put your fractures so that there is no interaction. Let me write what this LF is going to be. So this is going to be a minimum distance without fracture interaction. And well, this greater than equal is going to be a proportional sign. But I hope that you see it makes sense that the higher the pressure that you use, the higher is going to be the stress that you're going to impart on the rock, and so the higher is going to be the effect of a stress shadow. There is a variable that you can't see here in these plots, but it's going to be the fracture height. And by the way, I just remember, since talking about fracture height, so I have this little toy over here, which is this model of a wellbore with the planar hydraulic fractures. So this will be the distance between the fractures, right? And the hydraulic fracture height will be that. So usually these fractures tend to be longer than the fracture height. So this stress shadow effect is going to be also proportional to the fracture height. The higher the fracture height, this variable, the longer the stress shadow is going to propagate further out from the wellbore. And there is one more variable here that if you tell me which one that is, I'm going to give you triple extra points, but you cannot cheat, okay? You have to explain why. So we're saying that the minimum distance without interaction depends on how wide is your fracture, how high is your fracture. That's just geometry. But let me tell you, and the answer is related to this. We're looking for a distance so that the increase of stress that we apply does not make the stress to change direction, the minimum stress. We know in this case the minimum stress is this one. But if you apply too much stress due to propping a fracture, S3 might become, or in this case, the stress in east-west direction, which now is a minimum, might get larger than the stress in north-south direction. Because you apply too much stress in this direction, now you switch the stresses, and now the local stress is not anymore like the far field stress. So what do you think then we can put here that is going to be related to stress. Let me give you a hint. If you have a place where there is a large difference between SH min and SH max, then these problems of stress interaction are going to be not that serious, because it doesn't matter how much you increase SH min, then it's not going to overcome SH max. So what do you think we can put in here? It's going to have the units of pressure. Okay, I see that you guys probably have the answer, but you have looked at the answer in the notes. No?
In the notes. I'm like pretty sure it's S3 minus S1, but I wouldn't be able to explain why.
Okay, well, I'll just give you then one extra point.
Okay.
But it's actually, it's going to be S2 minus S3 to be positive. So in places with high, and in hydraulic fracturing world, this is called differential stress. In places with high differential stress, fracture interaction it's negligible or it's a lot lower. In places with small differential stress, just with a small perturbation of the minimum principal stress, you can make the fractures go in any direction and to go significantly non-planar. So in those places with small differential stress, you have to put your fractures further away, otherwise they're going to interact with each other. So let me just complete this with something else. I forgot to do this at the beginning, but let me do it right now. If this is distance over here, and here we have stress, next to a fracture, the variation of stress in direction, let's say east-west, to be to respect the coordinate system that we put over there, is going to decrease more or less with this shape, where the increase of stress right next to the fracture then is going to be the equivalent net pressure after you prop your fracture, and it's going to decrease very quickly, where this delta sigma is going to be proportional to the net pressure, the hydraulic fracture height, and it's going to be inversely proportional to the distance. So the further away you go, this stress influence is going to decrease. And just to write it down over here too, if the net pressure is smaller than the differential stress, you're going to have no fracture interaction. If the net pressure is higher than your differential stress, you might have fracture interaction. And again, the reason for that is that if you increase your pressure too much, your minimum principal stress is not going to be minimum anymore. It's going to pass to be the intermediate, and the one that was intermediate is going to become the minimum. So at the point at which you switch those stresses, then you start to have significant problems of fracture interaction. All right, so let's see some solutions for this. How we can mitigate the problems of fracture interaction. And we're going to take advantage of this problem in order to also introduce now a new concept and a new variable, which is going to be the distance between wellbores. So now we have we saw that we can design what is going to be the distance of the lateral. We can design what is going to be the distance between fractures. But now you can also set from a single path multiple wellbores, and you also have to design and see what is going to be the distance between wellbores. Okay, so if you're doing for example, a single cluster completion, just means you have one cluster per stage, something you can do is you can create one fracture here in this wellbore, simultaneously another one over here. In theory, those should not affect each other because they are far away and they are not next to each other. And then you could go ahead and place another fracture significantly far away so that they do not affect each other, and do, for example, number 2 here and 2' in this other wellbore. Again, we're looking at the top view. And after you do that, you could take advantage of these newly probed fractures and start one over here. So if you were to start a fracture without doing one and without doing two, probably this fracture would tend to turn in this direction if you have fracture interaction significant from number 2. But if you even out that increase of stress with number 2, in an ideal world of planar fractures, you could grow number 3 over here, and so on. So then you go 3, no, that will be 4, 4', and 5. And for example, this strategy is called, and it looks like that, it's called zipper fracturing. And you take advantage now of multiple wells in order to put these new fractures. So this will be horizontal wellbore number 1, horizontal wellbore number 2, and horizontal wellbore number 3. Let's add one more variable now to this problem. Sometimes you have net pays that are pretty high, and as we saw in some of those simulations before, the fractures are not going to, in general, they're not going to be evenly grow down and up, covering your entire net pay. Sometimes we assume that in simple models, but it doesn't really work like that in nature. So in order to take advantage of the full pay, you could place hydraulic fractures or horizontal wellbores which are offset in lateral distance and also in vertical distance. So here, and now this is a 3D block diagram where, let's say, here we have east, north, and down. You have wellbores that are offsetted in not only in lateral direction, but also in vertical direction. And in this way, you can take advantage of this. Let's try to draw a little bit more of realistic fractures. You could have a fracture somewhere over here, and another one. Usually you will put the stage a little bit, and not in the same plane here, but a little bit further, similar to the zipper fracture. but I find it a little bit difficult to draw that in this schematic. Let me see if I can do that. So if you were down here, then here you could grow another one, but now in this plane over here have other fracture growing on this plane. I hope you get the idea, but now you can also manage that geometry. And there is one more thing that I'd like to say over here, and is that there is another problem that when you have fractures that interact with other fractures, so the fluid that goes and interacts with another wellbore, that's what is called a fracture hit. You might be pumping in a wellbore, and then you realize that your gauge in other wellbore is measuring now an increase of pressure, and that's going to be a fracture hit. And of course, you have to design your distances between wellbores and spacing between wellbores so that you minimize this problem of hydraulic fracturing hit. Okay, let me see, what do we do next in the few minutes that we have? No, I think we're going to end here today, and on Friday we're going to talk about multi-stage, multi-cluster fracturing in a single stage. All right, so guys, just for organization, then remember we're going to finish with the lectures on Friday, and then Monday we're going to have a review for the exam. Okay, so make sure you do your homework, and then you have plenty of questions to ask on Monday. All right, see you then.